It's my pleasure to introduce our next speaker, Peter Atalla, who's the CEO and founder, president of Voxelmaps. And the Earth Archive is a very proud consumer of the Voxelmaps tech, and we're very excited to help in Peter's goal of creating a one-to-one volumetric digital twin of the Earth. And I'm always a little embarrassed. Peter's such a great speaker that I'm always a little embarrassed to have to follow him. Even today, that always seems to happen. So it's never a good idea to have the opening act overshadow the main act. But nonetheless, we'll persevere on. Thanks so much, Peter.
Thank you, Chris. Really appreciate it. You know, it's been amazing to see actually all of this come together in terms of the Earth Archive. So I met Chris and Steve probably about a year and a half ago, and just to see the work that's gone in from them, from everybody else to the first Congress has been absolutely incredible. So basically, what we're doing really at Voxelmaps, the way I'm structuring this presentation today is the first part of the presentation is going to be around Voxelmaps and voxel technology, kind of a 101 on voxels. The second part then is going to be the application to the Earth Archive and Earth Archive data. And we'll talk, about some of these really cool applications. So let's get started first with what we do. So everything we do at Voxel is around this concept of maps for machines. And I just want to explain the difference really between human maps and machine maps. So if we look at human maps, I mean, we're pretty all familiar with these, that the maps we have on our phone, they're in our cars, they're on our computers, and they're really around a use case of navigating people to addresses, whether that's a city, a street, or a building, or for visualizing data. So, creating some kind of geodata layers that we want to put on top. The majority of the data is really 2D. There are 3D elements, but it's not excessive, I would say, yet. And the accuracy of the data is relatively low. We're talking sort of 1 to 3 meters in terms of accuracy. What we do at Voxel is a little bit different. We're really focused on the concept of maps for machines. So here, these are true 3D spatial models. And we're analyzing every single object that we see in a given environment. So in a city, that's everything from the buildings to infrastructure, telecoms, utilities. In a non-urban area, that can be vegetation and land structures or land management. And we're doing this to a really high degree of accuracy. So 1 to 4 centimeters in terms of resolution. So try imagining, mapping the planet down to a 1 centimeter resolution in 3D. It's a big job. But it's not just about the location of objects. It's also about understanding the features and the attributes. So we're pulling back measurements, other data, which is incredibly important. And when I talk about machines, I mean everything from artificial intelligent models that are there to understand cities and to understand ecology and environments, all the way through to new forms of autonomy, whether that's autonomous vehicles or robots or drones. And there's a real requirement that this data exists everywhere, not just outdoors. So we're looking at indoor, subterranean data, even ocean data as well. So this is kind of the overall concept. Now, the goal of what we're trying to do, and when we first met the Earth Archive and listened to the TED Talk, it kind of blew us away because we were very interested in doing something very similar, but we were focused really on city and urban kind of environments. But the goal was to create a 4D volumetric twin of the Earth. And I want to take some time just to explain what I mean by that. So what do I mean by volumetric data? So 3D data, we've all seen. This is an example. This is taken from Google Maps, but there's lots of other great applications out there doing it as well. And these are really great visualization tools. They look very pretty. They're really good for humans. But when you really look at them, there's not a lot of information there. And what I mean by that, the majority of the 3D objects here are empty meshes. So it's a 3D mesh with something around it to make it look, very much like the object. But inherently, there's no information inside the structure. And you can see that when you zoom in. If you zoom in, you start to see pretty low accuracy data. So again, for visualization for humans, totally, great solution. But for some other applications, it's not as good. And really, when we're looking at, say, 3D meshes, what we're really doing here is if we have an object, if we have matter, we're only concerning ourselves with the surface of that matter. Whereas we all realize that matter, physical matter, has more than surface, it has interior volume as well. And sometimes that becomes very relevant. So volumetric data is addressing that. It's creating a 3D model that addresses not just the surface data, but the interior data as well. So within the same model, you can collect hyper-accurate information. For example, this is a city here being mapped to 1 centimeter voxels. But in exactly the same model, you can collect the interior space or the subterranean space, and that data will instantly drop into the model. There's no need for extensive post-processing, development of meshes, correcting textures, none of that. It just works. We combine this, as I said, with very high accuracy, so 1 to 4 centimeters, and we add a 4th dimension of time. And this is very important to do change detection, because while it's great to have a 3D environment, all of these environments around us change. And it's important we can have the ability to model that as well. So the way that we do this is we use voxels. And I'm sure a lot of you know of voxels, you've heard of voxels, but a voxel is a volumetric pixel. Essentially, it's a cube. And voxels aren't new. Voxels have been around for quite a long time. For example, Minecraft is an example of a computer game that is using voxels. But voxels have also been used in robotics. And there's areas of robotics that we were very focused on. So things around something called a VOG, a Voxel Occupancy Grid, which typically were kind of small dynamic maps of rooms for a small robot to kind of go in and navigate their way around them. So we took that concept, but we applied it to the planet. So it's an area of technology called MRVOGs, the multi-resolutional voxel occupancy grid. So we took the Earth and we placed a giant megavoxel over the top of the Earth. And this megavoxel is full of multi-resolutional voxels. Now, theoretically, they can be absolutely any size. But for our purposes currently, we use 8-meter voxels down to 1 centimeter voxels. And each voxel has a permanent position in space and has a unique address. And it's what we call an Earth-centered, Earth-fixed model. So it goes straight through the planet. It's subterranean, through the buildings, through the oceans, everywhere. But it's just a matrix. It's just a 3D, 4D georeference matrix. So what we have to do is we have to validate what we call the occupancy status of the voxel. Basically, is the voxel free space or is there matter inside it? So we do that using LiDAR. If the laser beam from the LiDAR passes through a voxel and it's not reflected off anything, it's free space, and we label it as such. But the moment that the laser beam is reflected off a surface, we collapse down to the smallest unit of the voxel, and we label this as occupied. So in essence, we're kind of etching out the matter of the planet as we go along. And we have the ability to collect this LiDAR data in all different ways, whether we're doing that from the ground with mobile mapping or even people with backpacks on, all the way through to different aerial platforms where we collect the data. Once we've got that, the platform that we've built is a global spatial database for this 3D and 4D data. We don't believe in 3D data just being a file that you load into some kind of viewer or some kind of tool for doing analysis and then load another file up for a different area. What we've built here is a real-time persistent model that's designed to scale to thousands of petabytes to be able to handle planetary scale data. And that's essentially what we're doing. So what does this data look like? So this is just occupancy status alone. It looks really similar to a point cloud. This was collected with one of our mobile mapping sensors. But this is all voxels. So these are all voxels. So with voxels, you start to have the shape, the measurements of everything. But on the surface of the voxels, you can put additional data layers. So for example, in cities, we very often use camera data. So we're putting the RGB values, the colors essentially on the voxels. So now you start to have something that looks more realistic to a human. But we can go beyond that. So unlike points or meshes, there's some really cool features really of the voxels. So firstly, each voxel is a volumetric measurement unit. So by default, it's very easy to perform calculations directly in the platform, as opposed to kind of transposing them into other data sets. I mentioned the surface data, and you can put different types of surface data on the voxels. And that doesn't just have to be camera data in terms of RGB. It can be hyperspectral imagery. It could be radar as well. You can create the map using that. So once you have the voxels, which kind of give the shape, and you have then the surface data, which in effect is color, you then apply artificial intelligent models deep learning models that really work in 3D. It's 3D semantic segmentation. So they look at these groups of voxels and they understand what they are. You train it to understand what it is, but not just in 3D. So every voxel has an infinite number of time states. So it has like a temporal data component. So you can get the AI to not only look at what's here at the moment, what's the current 3D picture, but if there's data for the past, you can ask it to look at the past and compare the two. So we have the ability then to do change detection, which becomes a really powerful feature. And so that when you merge that then with the addressing, with a global spatial database, with the ability to query and to search, it becomes an immensely powerful platform for all of this kind of data. So I want to give a quick example of an urban area of this data being applied, and then I'll come on to the second part of the presentation, which is really around the technology for the Earth Archive. So this is an example. This is occupancy status alone. This is downtown San Francisco in Embarcadero. This is with the camera surface data layered over the voxels. And then the colors that you now see here, this is actually the AI identifying the different features that it's interested in, and then classifying them. So these different colors that have appeared is the classification of the AI. And then automatically from that, we have the vectorization, which gives us a lot of flexibility in the data, which means we can now play around with the data. If we want to remove features, they're gone. We can focus just on the features of the environment, whether that's city or landscape that we're interested in, or put them back. It gives us a tremendously powerful way to look at this data and manipulate this data in real time, to analyze this in real time, versus going back to point clouds and doing processing, which takes a long time to do that. So that's all great. I mean, that's for cities, but what are we doing for the Earth Archive? So we've created a partnership with the Earth Archive where we've provided the Voxelmaps platform to the Earth Archive to host, to store all of the data, to process it, and also to provide some tools for the community then to start using in looking at some of the problems. So this is one example. This is aerial data that's been collected over Puerto Rico. So the data is first being voxelized. And once it's voxelized, then we can apply the artificial intelligence on it so we can detect the trees, obviously. And then we're removing the trees in the tree canopy with deep learning as opposed to some of the other methods. That gives us the ground plane. Clearly, it's not complete. So we reconstruct that in voxels. We can convert that to a mesh if that's beneficial. And so this really helps with things like digital elevation models, hydrology, soil mapping, other forms of land classification. So there's lots of applications around that. But we can also go a little bit further than this as well. So we have the ability to, using deep learning, actually count the individual trees, not just recognize the canopy, have a look at the individual trees themselves. So for example, in this sample of data that we have, there's just over 12,000 trees. So again, this is a great technology that could be used from the point of view of carbon accounting, or even forest health. And we hope to develop it that depending on the quality of the data, to be able to recognize individual species. So you'll be able to see some of these important changes. Some applications as well for archaeology. I mean, the project, the Earth Archive, started from that as well. So again, taking some data from the Earth Archive, we have voxelized that. This is in Mexico. Again, the artificial intelligence is removing the trees. That gives us the landform. We reconstruct the ground planes. And then what we've done here is we've actually trained AI to try and recognize features which we don't think are natural, which may hint that they might be archaeological. So these objects that have just appeared have been put there automatically. By no means is it perfect yet. It's very much in the very early stages of doing this kind of thing. But it's very interesting to see how big data sets could be analyzed using this kind of technology, using these kind of tools as well. Another example that I mentioned before is about change detection. Using same kind of data from Puerto Rico, we have a before and after scene. So this was actually before the Hurricane Maria, and then after the Hurricane Maria. So as well as being able to visualize the change, we can actually count what's happened. At the moment, we've been counting trees, but in the future, we have the ability to look at damage to buildings as well, not just the removal of an object, but the damage to an object as well. So again, really, interesting use cases. But the goal of what we're trying to do here with the Earth Archive is not a sales pitch. In fact, we're providing the platform entirely free for the Earth Archive. What we want to do is we want to empower the community, the Earth Archive community, to really get behind it and start to use some of these tools to go out and do some interesting things. So we have tools to automatically voxelize the data that is being provided, whether that's Earth Archive data or data that's being donated. All of the tool sets that you see will be available online, so you'll be able to access them via the web. We even have tools to train the artificial intelligent models. So in this video, there's a process called annotation. Here, somebody's training the AI to recognize trees. You have the ability to do this. You could go in and find objects that you're interested in and train some deep learning AI to go rapidly through data and find the objects that you're interested in as well. We even have some desktop tools as well, which are more designed for research applications. And there's already a VR viewer. So if you have a headset and you want to sit and walk through these forests and see things, you can absolutely do that as well. So just looking at the future, this is very much the beginning. This is the very first Congress as well. There's a lot of work to do. Mapping the planet is a huge, huge task. It involves partners and it involves a lot of people. But we're already looking at other forms of data. So one of the nice things, as I mentioned with the voxel model, is its multi-resolutional capability. So it's possible for us to take coarser resolution data and automatically ingest it and create these layers within the model as well. And so we're looking at satellite data, for example. In fact, Brian from NASA will touch on this in his presentation later on. We're also looking at 4D data sets. So data sets that have been collected multiple times of the same area, that we can really start to look at change and understand what that actually means. And also, and this is a very exciting area, looking at real-time models. So with APIs, we have the ability to pull in real-time data and represent that as layers in the voxel map or as things like voxel clouds. And this example here, this image here is actually 5G signal strength in a city that's been collected as a 4D data set and visualized as a cloud of voxels moving through a city. We can actually see the impact buildings have and actually track it even inside the buildings as well. So that kind of maybe climate data, maybe other forms of data that might be real-time or near to real-time could be really interesting. But as I mentioned, this is the beginning and we need your help. So we can't do all of this by ourselves. And today I want to make kind of a call out to people that might be interested in both the Earth Archive and this kind of technology. We're looking for interesting scientific questions, the big questions or the areas of interest where maybe this data could be applied to or these tools could be applied to. And around those questions, we want to create working groups of scientists, academics, volunteers that can devote some of their time to working out how we would go about trying to solve these problems or answer these questions. And from that, we want to create these challenges. And so the challenges will look at, can we answer some of these questions with this data, with these tools, or can we provide insight which could be valuable? So as I said, this is very much the beginning of the journey. I hope at the next Congress we'll have some great use cases and some challenges that we've been able to do with teams of people from around the world. But we're super excited to be part of it. And I'd be very happy to answer any questions if we have time. If not, please feel free to reach out to me afterwards. Be very happy to carry on the conversation.
Well, I hadn't seen that second half of that. So I'm trying to, that was amazing. I'm trying to digest that. That actually was the site of Angamuco in Michoacan, Mexico, central Mexico. And that was a pyramid and 2 walls and an altar that the AI identified. And I think if we play with that, we'll be able to pick out, there are probably 4,000 or 5,000 building foundations in that little tile alone. And we'll probably be able to pick out like a lot more of them. So I'm going to have to think about that, Peter.
Yeah, sorry, Chris, I should have shown you this before, but it's not perfect by any means, but it's a beginning and it shows promise. So
now I'm incredibly distracted, but we do have time for like maybe one question. So how do you generate your DL training sets?
So we collect the data ourselves. So actually back here, if we're looking at this this training set. In the city environment, we actually have our own vehicles that are driving around the world essentially at the moment. We collect for different customers about 1 million kilometers of data a year at the moment. So it's pretty big in terms of the scale. And so once we take that data in, we actually train ourselves. So we have teams that will go through and annotate. I mean, as I said, the annotation is in 3D. It's not a 2D semantic image that we're doing. It's a full 3D voxel annotation as well. So we annotate. Currently in cities, we're recognizing around 90 objects or so. And we've just really started in the ecology space and some of the archaeology stuff as well. And so that annotation process is one of the things that we really feel the Earth Archive community could be really great at. If there's objects they're interested in, we can give them the tools to train the AI and then see the results. That would be really exciting to see.